Quantum physics is a fascinating branch of physics that deals with the behavior of matter and energy on the atomic and subatomic level. It has revolutionized our understanding of the universe and challenged many of the assumptions that we hold about reality. The principles of quantum physics have led to some mind-bending concepts and theories that have transformed our view of the world. One of the most intriguing aspects of quantum physics is the idea that reality is not as objective as we once thought. According to quantum theory, the act of observation affects the behavior of subatomic particles, and the observer is an essential part of the experiment. This has led some physicists to conclude that the universe is not made up of objective, independent objects but rather a web of interconnected relationships that are shaped by the observer. This idea is best exemplified by the famous double-slit experiment, where a beam of particles is passed through two slits, creating an interference pattern on the other side. The experiment shows that particles behave like waves and can interfere with themselves, creating patterns that can only be explained by taking into account the observer's presence. When an observer measures which slit a particle passes through, the interference pattern disappears, and the particles behave like classical objects. This demonstrates that the observer's presence has a profound effect on the behavior of subatomic particles. This idea of subjective reality is a radical departure from the classical view of the world, where objects exist independently of our observation. In the quantum world, the observer is an essential part of the experiment, and the act of observation changes the nature of what is being observed. This has profound implications for our understanding of reality, consciousness, and the nature of the universe. Another intriguing concept in quantum physics is the idea of entanglement. This refers to a phenomenon where two particles become connected in such a way that the state of one particle is dependent on the state of the other, even if they are separated by vast distances. This connection is so strong that if you measure the state of one particle, it will instantaneously affect the state of the other, no matter how far apart they are. This effect is often referred to as spooky action at a distance, and it has been demonstrated in numerous experiments. Entanglement is a fundamental aspect of quantum physics, and it has profound implications for our understanding of space and time. It suggests that the universe is not made up of independent objects but rather a web of interconnected relationships that transcend space and time. This has led some physicists to propose that the universe is a hologram, where the information that makes up our reality is encoded in 2 dimensions and projected into 3 dimensions. The idea of a holographic universe is still a subject of debate, but it illustrates the far-reaching implications of quantum physics. It challenges our assumptions about the nature of space and time, and it suggests that our reality is more fluid and dynamic than we once thought. The principles of quantum physics have also led to the development of many technologies that have transformed our world. One of the most well-known applications of quantum physics is in the field of computing. Quantum computers use the principles of entanglement and superposition to perform calculations that are impossible with classical computers. This has the potential to revolutionize fields such as cryptography, finance, and drug discovery. Quantum physics has also led to the development of technologies such as quantum cryptography, quantum teleportation, and quantum sensors. These technologies are based on the principles of entanglement and superposition and have the potential to transform many fields, including telecommunications, medicine, and environmental monitoring. One of the most famous quantum paradoxes is the Schrödinger's cat experiment, which illustrates the strange behavior of subatomic particles. In the experiment, a cat is placed inside a box with a radioactive substance that has a 50-50 chance of decaying in an hour. If the substance decays, it triggers a mechanism that releases a poison that kills the cat. According to quantum theory, the radioactive substance exists in a state of superposition, where it is both decayed and not decayed at the same time. This means that the cat is also in a state of superposition, where it is both alive and dead at the same time. It is only when the box is opened and the observer makes a measurement that the cat's state becomes definite. This paradox illustrates the idea of superposition, where particles can exist in multiple states simultaneously. It also demonstrates the idea of the observer's role in quantum physics, where the act of observation collapses the wave function and forces the particle to assume a definite state. Another famous paradox is the EPR paradox, named after its discoverers, Einstein, Podolsky, and Rosen. This paradox illustrates the idea of entanglement, where two particles can become connected in such a way that the state of one particle is dependent on the state of the other. The paradox arises when you consider what happens when you measure one of the particles. According to quantum theory, the measurement collapses the wave function, and the state of the other particle becomes definite, no matter how far apart they are. The EPR paradox has been the subject of intense debate, and it has led to some of the most significant advances in quantum physics. It has also led to the development of the Bell's inequality, which is used to test for the presence of entanglement in quantum systems. The principles of quantum physics have also challenged our understanding of time. In classical physics, time is considered to be a universal constant that moves forward at a constant rate. However, in the quantum world, time is more fluid and dynamic. According to quantum theory, particles can exist in a state of superposition, where they are both in the past and in the future at the same time. This has led some physicists to propose that the universe is timeless and that time is an emergent property of the universe. The concept of time has also been challenged by the idea of quantum tunneling, where particles can tunnel through barriers that would be impossible to cross in classical physics. This suggests that particles can move from one point to another without traveling through the intervening space, which challenges our understanding of space and time. Quantum physics has not only challenged our understanding of the universe, but it has also opened up the possibility of new technologies that were once thought to be science fiction. One of these technologies is quantum teleportation, which involves the transfer of information from one location to another without physically moving the information through space. Quantum teleportation is based on the principle of entanglement, where two particles become connected in such a way that the state of one particle is dependent on the state of the other. This means that if you measure one particle, the state of the other particle becomes definite, even if they are separated by vast distances. In quantum teleportation, a third particle is used as a messenger to transfer the state of the first particle to the second particle. The messenger particle becomes entangled with the first particle, and its state is then transmitted to the second particle. This process is repeated until the entire state of the first particle is transferred to the second particle. This allows for the transfer of information without physically moving it through space. Quantum teleportation has the potential to revolutionize communication and computing, and it has already been demonstrated in the laboratory. However, there are still many challenges that need to be overcome before it can be used in practical applications. Another area where quantum physics has the potential to transform technology is in the field of brain-machine interfaces. Brain-machine interfaces involve connecting the brain to a computer to allow for the direct control of machines or to provide feedback to the brain. In the past, brain-machine interfaces were limited by the low resolution and speed of the technology. However, advances in quantum computing and quantum sensors have the potential to revolutionize brain-machine interfaces by allowing for higher resolution and faster processing. One potential application of quantum brain-machine interfaces is in the development of prosthetic limbs that are controlled directly by the brain. This would allow for more natural and intuitive control of the prosthetic and could significantly improve the quality of life for amputees. Another potential application is in the development of brain implants that could help restore lost functions, such as hearing or vision. These implants could interface directly with the brain and provide the brain with the necessary information to restore these functions. However, the development of quantum brain-machine interfaces also raises important ethical questions, particularly around the issue of privacy. The ability to directly access and manipulate the brain raises the possibility of mind reading and mind control, which could be used for nefarious purposes. Quantum computing is another area where quantum physics has the potential to revolutionize technology. Traditional computers use bits to store and process information, with each bit representing either a 0 or a 1. Quantum computers, on the other hand, use quantum bits, or qubits, which can represent both 0 and 1 at the same time. This property of qubits allows quantum computers to perform certain calculations much faster than traditional computers. For example, a quantum computer could quickly factor large numbers, which is a task that is very difficult for traditional computers. This could have major implications for cryptography, as many encryption algorithms rely on the difficulty of factoring large numbers. However, quantum computing is still in its infancy, and there are many technical challenges that need to be overcome before it can be used in practical applications. One of the main challenges is the issue of decoherence, which refers to the fact that qubits are very sensitive to their environment and can easily become entangled with other particles, which can cause errors in the computation. Despite these challenges, there has been significant progress in the development of quantum computers, and many tech companies, including Google and IBM, are investing in the technology. It is still unclear what the ultimate impact of quantum computing will be, but it has the potential to transform a wide range of industries, from finance to medicine to energy. Another area where quantum physics has the potential to transform technology is in the field of cryptography. Cryptography involves the use of mathematical algorithms to secure communication and protect sensitive information. Many of these algorithms rely on the difficulty of certain mathematical problems, such as factoring large numbers or computing discrete logarithms. However, quantum computers have the potential to solve these problems much faster than traditional computers, which could render many encryption algorithms vulnerable to attack. This has led to the development of post-quantum cryptography, which involves the development of new encryption algorithms that are resistant to quantum attacks. One of the most promising post-quantum cryptography schemes is based on the use of lattice-based cryptography. This involves the use of complex mathematical structures called lattices to encode information. The security of lattice-based cryptography is based on the difficulty of finding short vectors in high-dimensional lattices, which is a problem that is believed to be difficult even for quantum computers. Quantum entanglement is one of the most fascinating and mysterious phenomena in physics. It is a phenomenon where two particles become linked in such a way that the state of one particle is dependent on the state of the other, even if they are separated by great distances. This phenomenon challenges our classical understanding of cause and effect, and has important implications for the study of quantum mechanics. The EPR paradox was proposed as a challenge to the theory of quantum mechanics, which was still in its early stages at the time. Einstein, Podolsky, and Rosen argued that the theory of quantum mechanics was incomplete because it allowed for non-local effects like entanglement, which violated the principle of locality. They proposed that there must be some hidden variables that determine the state of particles, and that the theory of quantum mechanics was missing something important. However, subsequent experiments have shown that the phenomenon of entanglement is real, and that it cannot be explained by any classical theory. In fact, entanglement has been experimentally demonstrated many times, and it has important practical applications in fields such as quantum cryptography and quantum computing. One of the most fascinating aspects of entanglement is the fact that it can exist between particles of any type, including atoms, molecules, and even large objects. This has led to the idea of quantum superposition, where objects can exist in multiple states at the same time. The phenomenon of quantum superposition is the basis of quantum computing, which promises to revolutionize the way we process and analyze data. Entanglement has also led to the development of new theories of quantum mechanics, such as the many-worlds interpretation and the transactional interpretation. These theories propose that the universe consists of multiple parallel realities, each corresponding to a different outcome of a quantum event. In this way, entanglement has challenged our classical understanding of reality, and opened up new avenues for exploration and discovery. In conclusion, quantum entanglement is one of the most fascinating and mysterious phenomena in physics. It challenges our classical understanding of causality and locality, and has important implications for the study of quantum mechanics. The EPR paradox, proposed by Einstein, Podolsky, and Rosen, was a thought experiment designed to challenge the theory of quantum mechanics, but subsequent experiments have shown that entanglement is real, and that it has important practical applications in fields such as quantum computing and cryptography. As we continue to explore the quantum world, we are sure to uncover even more mind-bending and fascinating concepts that will transform our understanding of the universe and ourselves. In this video, we have explored the fascinating world of quantum physics and its implications for our understanding of reality. From the strange behavior of subatomic particles to the mind-bending concepts of entanglement and superposition, we have seen how quantum physics challenges many of our preconceived notions about the universe. We have also looked at some of the practical applications of quantum physics, such as quantum computing and cryptography, and how they may shape the future of technology. But perhaps the most profound aspect of quantum physics is its philosophical implications. The concept of observer-dependent reality, as embodied in the measurement problem and the EPR paradox, forces us to rethink our assumptions about the nature of existence itself. If you enjoyed this video, please like, subscribe, and leave a comment below with your thoughts and feedback. Thank you for joining us on this journey through the world of quantum physics.